right, so I want to talk about one of my favorite topics, which is isotopes. Isotopes, aside from being the name of a baseball team, is a term for when you're talking about a collection of atoms, all of the same element, but with a specific number of neutrons. This will make more sense as you see the math of what's going on. All right, so just a review. When we're looking at an element tile on the periodic table, we have these pieces of information. You have the atomic number at the top, which tells you the number of protons you have for that element. We're going to be working mostly with the example of carbon today. Carbon, by definition, is an atom with 6 protons in it. Here at the bottom, we have the atomic mass. I like to think of it as a weighted average of atomic masses for the different isotopes. Carbon has mostly carbon-12, okay, as I write here. Carbon-12 is 99% of the carbon on Earth. And that 12 comes from having 6 protons and 6 neutrons in its nucleus. 6 plus 6, you get that number 12. All right. 1% of the carbon on Earth, approximately, is carbon-13. That comes from having 6 protons and 7 neutrons. 6 plus 7, you get 13. Now, that word weighted and weighted average can confuse people. Weighting in a mathematical sense just means that since the 99% of the carbon-12 is the dominant form of carbon, the average is going to skew closer to the 12. We see that here. 12.011, that's the weighted average. That's the atomic mass of carbon. We can see that on average, it's going to be closer to 12 because we have more of the carbon-12. You can't simply just add 12 and 13, get 25, divide by 2, and get 12 and a half, because that wouldn't accurately reflect that most of the carbon is carbon-12. Hopefully that makes sense. Okay, so yeah, those are the two main isotopes of carbon on Earth. There's also a little bit of carbon-14 coming from cosmic radiation. That's the radioactive form of carbon we have on Earth. Thankfully, that's only about like 1 in a million carbon atoms or so. And that's useful for when people are doing radiometric dating, such as carbon dating, to figure out the time since an organic organism, a carbon-containing thing, passed away. All right, so there's applications for all this. All right, anywho, so let's get on with it. This is going to be our isotope symbol template. X just meaning whatever your element symbol is. I got some examples here if you want to look at those. So for carbon, we would just put a C here. And then some new terminology. So Z is the number of protons, also known as the atomic number. We may have heard of that one before, but A is often a new one for many. That's called the mass number. Mass number is not the actual mass. You're not like weighing it or anything like that. I mean, it'll be close to that weight or mass, but it's actually just a pure counting number. It's actually an exact number, just like Z is an exact number. To get the the mass number, you're going to add the number of protons, the atomic number, and you're going to add N, which is the number of neutrons. There. Okay, so you add up your number of protons, your number of neutrons, and you get this thing called the mass number. Now, N, the number of neutrons, usually is not put on the isotope symbol. And that's because people who work in the nuclear fields, radiochemists, nuclear physicists, chemists, we often actually don't really need that number of neutrons. we're often more interested in just the overall contribution to mass, the mass number, than the specific number of neutrons. That being said, sometimes we do need that number, so it's important that you know how to calculate it. So let me slide this over. So we got some examples with carbon. Actually, I'll just shrink this. Hopefully the lip reading is still okay. There we go. So we talked about those 3 different isotopes of carbon earlier, carbon 12, carbon 13, carbon 14. Using this template, here's how we would write out those symbols. At the bottom left, we write the number of protons, the atomic number Z. And at the top left, we write the mass number. You can see that when we're talking about a specific isotope, we say the name, and then we say the mass number. We don't mention in the name of the isotope, we don't mention the Z, the number of protons. And that's because you can already tell what that is just from the name alone. So for carbon 12, put a 6 there, you put a 12 there. If you're interested in calculating the number of neutrons, you would use this formula here. You would rearrange it so that's N equals A minus Z, 12 minus 6, and we get that 6. All right, so for carbon 12, the dominant form of carbon on Earth, it has the same number of protons as neutrons. All right, so for the remainder of this video, let's do some examples together. First, we're going to create some isotope symbols together, and then we're going to look at some symbols and give the A, Z, and N values for those. All right, so we have first uranium-235. This will require us to have a periodic table handy. ptable.com is I like to go to this place, easy to read. So let's look for uranium. Uranium is element number 92. There is that weighted average at the bottom, 238.03, but that's taking all uranium isotopes into consideration. So we don't have to actually worry about that number too much when we're working with isotopes, specific isotopes. All right, so I'm going to write, let's take a different color pen so you can see my answers. Of course, pause this video to work on these on your own first, and then we'll compare. All right, so we got a Z of 92. Same for the next problem. So we'd go 235, 92, and then we'll put a U. For uranium-238, similar answer. How about cesium-137? Let's look up cesium. CS. And I guess cesium can also be spelled like that. All right, so cesium was element 55. We have 137. CS. All right, strontium 90. There's strontium. Number 38. All right, and you may have seen earlier, like here, I showed the isotope symbols without the atomic number Z. That is an option for writing out an isotope symbol, because just from the symbol, you'll already know what the element is, and therefore you know how many protons it has. For starting out, I recommend you do it this way, and then with some practice, that should be something you should be able to do as well. All right, let's keep going. So we got fluorine 18. All right, fluorine is element number 9. And then we have technetium 99. Technetium is the first artificial element appearing on the periodic table. 43 is the earliest instance you have that. And there's technetium 99. All right, let's move to these examples. All right, in the previous examples, we weren't concerned with the neutron number, but we'll work that into our analysis this time. So to change it up, I gave isotope symbols. So those are already made for us. We're just going to now extract the information from those isotope symbols. All right, and we can color code and shape code this. I'll like that, red boxes for those. Just to remind ourselves that we don't have to calculate that. It's already provided. I'll do the same thing with the Z's. I'll use green circles. And then for the N's, well, that doesn't go into isotope symbol, so we will have to calculate that. Okay, so spend a minute or two working on these, and then you can compare with my answers. All right, here are my answers. All right, so here we have protium. This is the most dominant form of hydrogen, not just on Earth, but in the universe. All right, protium just having a mass number of 1. Okay, so this is hydrogen 1. That's most hydrogen. Here we have hydrogen 2, also known as deuterium. And here we have hydrogen 3, also known as tritium. Right? But again, most hydrogen in this form, these two, if you're curious about it, are stable, whereas this tritium is radioactive. All right, let's calculate. A, Z, N. When I have multiple on the same page, I just like to set all this up. All right, so hydrogen 1 has a mass number of 1. It has 1 proton. 1 minus 1 equals 0. Okay, maybe I should have rewritten the formula somewhere just to remind you. We get it from A minus Z. So this is interesting. Hydrogen 1 has no neutrons. No neutrons. All right. This is rare. This is the only instance of a stable element, a stable isotope, having no neutrons whatsoever. Okay. So in fact, if I had a neutral atom of hydrogen 1, but then I knocked off one of its electrons, it would only have a proton left. So the nickname for a hydrogen ion is a proton. All right, let's keep this going. Hydrogen 2, mass number of 2, still just 1 proton because it's hydrogen. So we're going to do 2 minus 1, 1 neutron. All right, so deuterium has a mass number of 2 as a result of having 1 proton and 1 neutron. All right, we got hydrogen 3. With 2 neutrons. All right, let's do some oxygen stuff. So that's oxygen 16. Here we have oxygen 17. All right. And then lastly, oxygen 18. All right, there we go. All right, got one last final thought in case the definition of isotope wasn't fully clear. Okay, so once again, if I'm referring to a specific isotope, I'm referring to just something with some set number of protons and some set number of neutrons. That's if we're saying isotope singular. If we're saying isotopes plural, you may be referring to a set of atoms of the same element but with different numbers of neutrons. In other words, right here we have a set of isotopes. These are two different boron isotopes. In order to be called isotopes, you have to be the same element. But they have different number of neutrons, so they're isotopes because you can have the same. You have to have the same Z, but you can be different in your number of neutrons and therefore your mass number. All right, to be an isobar, this is not a term we use too much in Chem 101, so I wouldn't worry a ton about it. I'm just putting it out there so you can help form a better definition of isotope. But if you're interested, an isobar is when you have two things with the same mass number, but you have a different elemental identity. In other words, you have a different Z. So right here, we have potassium 40 and calcium 40. They have the same mass number, but they're not the same element. So those would be isobars. But again, at the Chem 101 level, we're usually talking about isotopes more than isobars. All right, hope this helps. Have a great day, and any questions, leave them in the comments, leave comments in the comments, whatever. All right, thanks, bye.